This video is part of the MCAT Chemistry video course. Subscribe and hit the bell if you'd like notifications about the release of new videos, and please visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we'll cover how to calculate the pH when you're given a strong or a weak acid. First, we'll go over how to solve strong acid-base problems, and you need to first recognize that strong acids or strong bases will completely react. So if you look at something like HCl, and the reaction for HCl we have written right there, and just remember that we could also write this as HCl plus H2O gives us the hydronium ion plus Cl minus. So remember that both of those are completely valid ways to write that reaction. And remember that the Ka tells us how many of our products are going to be made. The Ka for something that's a strong acid like HCl is an extremely large number because the exponent there is a positive 6. So that's a huge number, which means virtually every single molecule of HCl is going to react. So the concentration of the H plus ions is just going to be equal to the concentration of the acid that we put into the solution in the first place. So let's look at this strong acid problem down here where we have 1 times 10 to the negative 5 moles of HCl placed in 2 liters of water. You don't need to go through this process every time, but I just want to be clear on exactly what the thinking is. So starting on the left, just write your reaction. So we're starting with 1 times 10 to the negative 5 moles of HCl. And after just a little bit, all of those molecules of HCl will dissociate into the hydrogen and the chloride ions. So then give it a little bit of time. There's no more HCl left, but there is hydrogen and there is the chloride ions. And there will be 1 times 10 to the negative 5 moles of each of those. We are worried about the concentration for H, not just the moles of H. So right now we have the moles of H, but we need to find the concentration. So we do 1 times 10 to the negative 5 moles divided by the 2 liters, which is going to give us 0.5 times 10 to the negative 5 molarity. And I would get the 0.5 right here into a whole number. So change that to 5 times 10 to the negative 6 molarity. Now calculate pH like we talked about in the last video. So that would be negative log of 5 times 10 to the negative 6 equals pH. So 10 to the negative pH equals 5 times 10 to the negative 6. And remember from the last video, whenever you have something like 1 times 10 to the negative 6, it's a fairly easy problem to solve because the pH is just equal to whatever your exponent is. So we want to figure out what 2 values is 5 times 10 to the negative 6 in between, and pick 2 values that would be super simple to solve. So 5 times 10 to the negative 6 is a greater value than 1 times 10 to the negative 6. And then 5 times 10 to the negative 6 is a smaller value than 1 times 10 to the negative 5. So for the 1 times 10 to the negative 6, the pH would equal 6. For the 1 times 10 to the negative 5, the pH would equal 5. We've already established that our number is in between those 2 values. So you can just choose pretty much any number between those 2. I'll just go with 5.5, and you're going to be close enough to pick an answer option out of the 4 that are going to be given to you. So the pH for this one would be about 5.5. So strong acid problems are pretty straightforward because the concentration is just straight up whatever concentration of the acid is given to you. The hardest part is going to be memorizing your strong acids. I would just start with these acids that are listed here, which this list may be shorter than some others that you've seen, but these are going to be the most common acids that you see on the test by far. It's pretty easy to memorize because we have halogen-based acids on the left, and keep in mind that you don't see a fluorine-based acid. And that's because fluorine is actually going to be a strong enough base that it'll be a weak acid instead of a strong acid like these. And then you only have 2 other acids that you need to memorize, which would be nitric acid and sulfuric acid. Next, let's look at the strong base problems. And the strong base problems add one little additional thing to it, and we will illustrate that right now with our example. But the concentration of OH minus is what we're going to be looking for with these strong bases. And that's equal to the concentration of the base times the equivalence of OH minus. And let's look at the second problem to show what we mean by that. So if These moles of calcium oxide are placed in 1 liter of water. We need to calculate the pH. So remember that we can find the pH once we have the pOH. So let's just first go with solving for the pOH. So we have 1.2 times 10 to the negative 2 moles of calcium oxide in 1 liter of water. So that means that the concentration of calcium oxide is 1 times 10 to the negative 2 molar. But you need to notice that there are 2 molecules of oxide for every 1 molecule of calcium oxide. So that means that our concentration of oxide is going to be double the concentration of calcium oxide. So the OH concentration is equal to 2 times 10 to the negative 2 molar. So now find the pOH, which is the negative log of the OH concentration equals the pOH. Solve this the exact same way as the pH problem. So you do 10 to the negative pOH equals the concentration of hydroxide, which is 2 times 10 to the negative 2 molar. Think about this the exact same way as we did the pH problem. So we need to think what 2 easy numbers is 2 times 10 to the negative 2 between. So 2 times 10 to the negative 2 is greater than 1 times 10 to the negative 2, but it's less than 1 times 10 to the negative 1. So that means that our pOH needs to be between 2 and 1. So you could pick something like 1.5, and you're probably going to be totally fine for the test. You could also try to go a little bit more precise and ask yourself, is 2 times 10 to the negative 2 closer to the number on the left or the number on the right? And hopefully you can see that it's closer to the number on the left, because the number on the right, to be really close to that number, you would need something like 9 times 10 to the negative 2. So if you wanted to be more precise, you could do something like pOH equals 1.8, and you might be a little bit closer. But either way, you're going to be fine. Now to find the pH, remember that pOH plus pH equals 14. So then the pH is equal to 14 minus 1.8, which equals 12.2. Your strong bases are really straightforward to memorize because you have just group 1 metal-based bases and then group 2 metal-based bases. And remember that group 1 metals have a +1 charge and OH has a -1 charge. So for the group 1 metals, there's only 1 hydroxide ion for each base. For the group 2 bases, there are 2 hydroxide ions for each base because group 2 metals have a +2 charge. So you're going to need 2 molecules of the hydroxide ion to balance out that +2 charge. Finally, we have a weak acid problem, and a weak acid problem is a classic use of an ice table, which by the time you get really used to using these, you probably aren't going to need to actually do the ice table, but it's really good practice, and if you cannot do an ice table, then I would say you don't have a full mastery of this topic, so make sure you can do one if needed. So remember that Ka is equal to products over reactants, but we don't include water, so that would be the concentration of F- times the concentration of the hydronium ion over the concentration of HF. So we are trying to find these values to plug into this equation, and that's what the ice table is for. To properly do the ice table, you need to figure out what your initial concentration is of your acid, and the problem tells us that we have a 3 molar concentration of HF. So we put a 3 in there for HF. That's our initial concentration, so we have 0 of the products because no time has passed to allow HF to dissociate. After some time has passed, some HF has dissociated, but not all of it. So we do minus X. However many molecules of HF dissociate, that produces that many molecules of F- and H3O+. So we do plus X because those values will be equal. And then at the end for the equilibrium, you just combine your values. So we end up with 3 minus X and then just X for our products. Now you plug those values into your equation for Ka. We end up with Ka equals X times X over 3 minus X. Ka is 3.5 times 10 to the negative 4, and so that's going to equal that equation above. And this is a weak acid, so X is not going to be a very large number. So when we take this term 3 minus X, and if we were to actually subtract X from it, we're going to end up with a number that's like 2.99 something. So there's no need to actually subtract x from the 3. So we can just cross that out, and we're not going to need it. So what we end up with is x squared on top and then 3 in the denominator. And now we have a much easier problem. So x squared equals 10.5, because 3 times 3.5 is 10.5, times 10 to the negative 4. And now you have to figure out what's the square root of 10.5 times 10 to the negative 4. And always do these in the individual parts. So you do what's the square root of 10, and then what's the square root of 10 to the negative 4. 10.5 is pretty close to 9, so you can round that on the test pretty easily to just 3. So you'd have 3 times the square root of 10 to the negative 4. And remember, whenever you take the square root of an exponent, you're just dividing it by 2. So negative 4 divided by 2 equals 2. And anytime you take the square root of an exponent, you're just dividing it by 2. So negative 4 divided by 2 equals negative 2. So you end up with 3 times 10 to the negative 2. And we already established that the concentration of H3O is just straight up equal to X. So the concentration of H3O plus equals 3 times 10 to the negative 2. We've established in a previous video that H3O is synonymous with H+, so then we can just equate that to the concentration of H+, and then now just solve for the pH like we normally do once we have the concentration of H+. So we do negative log of 3 times 10 to the negative 2 equals pH. So 10 to the negative pH equals 3 times 10 to the negative 2. 3 times 10 to the negative 2 is greater than 1 times 10 to the negative 2, but it's less than 1 times 10 to the negative 1. So we're dealing with a pH between 2 and 1. So you'd be totally fine to say that this pH is about 1.5. And for a weak base, you'd apply the exact same approach. Just make sure that you're using the KB whenever you're trying to solve for the OH concentration.